Hello all, welcome to my course on methods of adhesion measurement, theory and practice. Today we are at lecture 21 and we are discussing about surface energy, interfacial energy. In the last lecture I discussed that how to estimate the interfacial energy between two different materials 1 and 2 which are either in vacuum or immersed in medium 3. So, we derived this expression of interaction energy delta F 132 and this is the Lipschitz van der Waals component and it is given like this. And then we also presented this particular equation Young's equation without giving the proof that how it works, how it is derived, but then we use this Young's equation with what is known as this Good-Girifalco equation to derive what is known as this Young-Dupré equation. So, this Good-Girifalco equation that considers both the Lipschitz van der Waals component and the polar component of surface energy. So, gamma S or gamma L will be given as gamma S LW plus gamma S P plus gamma S P. So, so it considers both this Lipschitz van der Waals component and the polar component and the interfacial energy between these two materials, let us say solid and liquid, which are given by this equation. And I also solved some problems based on that, and then we can combine this Young's equation and the Good-Girifalco equation to derive this Young-Dupré equation. So, we have shown all that. So, today I am going to discuss about this Young's equation and how to obtain that. That will be the today's topic, the how to obtain the Young's equation and surface tension of liquid. So, in essence what we have is something like this: a liquid drop is dispensed on a surface and then you let this particular drop come to equilibrium, and what you measure is known as the equilibrium contact angle, that the tangent of this particular tangent to this point at the 3-phase contact line that you can drop, and the tangent makes an angle with the horizontal surface. So, that angle is called the equilibrium contact angle. So, in this case we will consider only the advancing contact angle, because you have dispensed the liquid and allowed the liquid to spread and then come to rest, that is the equilibrium condition. So, how to estimate or how to determine this equilibrium contact angle. So, equilibrium contact angle will be determined by this minimization of the total energy of the system. So, what are the different energy components? So, we have these are all surface energies. We will not worry about the gravitational energy or potential energy of this particular drop, that is not required here. Now, here this particular drop has got this surface area that is represented by this curved surface, that is represented by this AL here. So, the AL you represent AL into gamma L is the surface energy of the liquid. So, the gamma L is the surface energy per unit area of the curved surface of the liquid. So, that is gamma L into AL, and then we have this interface between the solid and liquid. So, that is given by this ASL. So, that is this amount of an area that is covered by the weighted area of the solid that is covered by this particular liquid, that is this ASL multiplied by gamma SL is the interfacial energy between solid and liquid. And then you have this proportion which is actually outside, which was the total area minus the surface interfacial area between the solid and liquid. So, that is AT is the total minus ASL. So, AT minus ASL defines the solid surface on the outside this weighted area of this particular liquid. So, that is this quantity AT minus ASL, and that is the solid surface. So, we multiplied by gamma S. So, the total energy of the system is given by this particular equation. Now, I will minimize the total energy by two different methods. One is somewhat approximate, and then I will present a more rigorous analysis. So, in the approximate analysis, so what you do is that you estimate the del pi by del ASL. So, total is the pi is the total energy, and when you do that let me write it, it will be better. So, del pi by del ASL. So, that will equal to minus of gamma plus this gamma SL and plus this gamma L into delta AL by delta ASL, like that. So, so now we have to estimate this quantity del ASL by del AL by del ASL, and that we can do by considering the following. We actually can consider something like this, that this is the solid surface, and let us say this is the 3 phase contact line, and let us say that the 3 phase contact line has moved by a distance, that is delta ASL. So, because it has moved here, it has changed something like this, the profile of this liquid drop changed something like this, let us say. And so, therefore, we can actually draw a perpendicular over here, and so these are infinitesimal distance. So, the change in the surface area of the liquid is over here, delta AL. So, you see this is perpendicular 90 degree, this angle is theta because it is very close to this angle. This particular contact line has moved in this direction by this very small infinitesimal distance. So, therefore, this quantity delta AL divided by delta ASL. So, that is actually cos of this particular angle, which is theta equilibrium. So, this is equal to cos of theta equilibrium, and so you substitute over here and you get here minus or gamma S is equal to gamma SL plus gamma L cos theta equilibrium. That is basically the Young's equation that I have written earlier. So, here as you can see, we have presented in somewhat approximate manner this particular quantity here, this A delta L by delta SL is equal to cos theta equilibrium. So, we can actually so but then it shows it we can present or we can get this Young's equation, okay, by this analysis anyway, but we can actually do this thing little bit differently, more rigorously. So, that is what I am going to do. So, here let us say that we have got this particular liquid drop on this particular surface. So, suppose here something like this, and we will consider that this liquid drop is small enough that it forms a spherical cap. So, it is part of a sphere, that is all we will consider, and let us say that this is the vertical line and then this is the tangent over here. So, therefore, this is the angle theta. So, what I am going to do is, this is let us say A here, and we can actually draw this. So, this is the center of that particular circle, this is the radius of this particular circle, the height of this particular drop is let us say h here. So, if you can if you see, this is the radius of this particular circle. So, this whole angle is 90 degree, right. So, if this is 90 degree, so then this angle is 90 degree minus theta, this is 90 degree. So, therefore, this angle will be theta. Again this whole angle is, this angle is theta and this angle is 90 degree. So, this angle will be 90 degree minus theta, this is 90 degree minus theta. Since this is 90 degree, so therefore, this angle will be theta here. So, therefore, this quantity A will be equal to r of sin theta, and h is equal to r minus r of cos theta. So, it is h is equal to r into 1 minus cos theta. So, like that. So, in essence here also we will like to find out the total surface energy of this particular liquid drop. So, we have to somehow have the idea of this circular or this spherical cap, what is the surface area of this spherical cap, and we have to remember that this liquid drop attains this equilibrium contact angle, okay, under the constraint that its volume remains constant, okay, its volume has to remain constant. So, we have to estimate the curved surface area of this liquid drop, this weighted area, okay, and which is weighted by, that is this weighted area, and then also we have to obtain the volume. So, that we get from the geometry of a spherical cap. So, it is like this, the surface area, okay, of this particular liquid drop AL is given as pi into a square plus h square. So, like that. So, this is the A I drew and this is the r, this is the theta I had shown, and this is h. So, surface area is given as pi into a square plus h square, let us write everything in terms of r and theta. So, this is pi and a square is r square, this is sin square theta plus h square. So, that is 1 minus cos theta whole square. So, this quantity will be pi into r square into 1 let us say sin square theta plus 1 minus 2 cos theta plus cos square theta. So, this will be equal to this 1 plus sin square theta plus 1. So, 1 plus 1 is 2 and 2 goes over here. So, it is 2 pi r square into 1 minus cos theta, and this is ASL, that is pi a square. So, it is pi and a is r sin theta. So, it is r square sin square theta. So, like that. Now, we have this. Now, surface area of the solid is AT minus ASL. So, we have to write simply here AT minus pi r square and sin square theta, and the totals, therefore, the total energy of this particular drop and system very same way, very similar to the way that I had written earlier. So, this will be equal to gamma L into AL. So, it is gamma L into 2 pi r square into 1 minus cos theta, okay, plus gamma SL into ASL. So, gamma SL into pi r square sin square theta, and plus this is gamma S into AS. So, gamma S into AS is AT minus ASL. So, it will be AT minus pi r square sin square theta. So, if I write in a little bit more compact form, it will be gamma L into 2 pi r square 1 minus cos theta plus this is gamma SL minus gamma S. So, it is gamma SL minus gamma S into pi r square sin square theta plus this is gamma S into AT. It will be like this. Now, I have to worry about the volume of the spherical cap. So, volume of the spherical cap is given by pi by h 3 a square plus h square. So, you substitute here for a and h. So, it is pi h by 6 into 3 a square sin square theta. So, a is equal to r sin theta. So, it is r square sin square theta and plus h square is r square into 1 minus cos theta whole square, okay, like that. So, after taking into account all the other terms and all that, okay, we will get here of course, h also have to substitute r into 1 minus cos theta. So, h also we have to substitute here r into 1 minus cos theta here. So, do all that and then you find out finally like this V in terms of r and theta. So, essentially what we have done is that we have considered this spherical cap, this angle is theta, and all the dimensions a, h we have actually written in terms of r, capital R and theta, and then we have obtained this. So, we have now the expression for the total energy that we have it here, and we have the expression for the volume. So, now what we need to do is to minimize this total energy under the constraint that this volume remains constant. Okay. So, that is all we need to do now. So, this particular kind of problem is called constraint energy minimization. Constraint energy minimization, that is what we are going to do, energy minimization. This is the problem that we have. So, the problem that we have here is actually quite simple, because we have only r and theta, there is no derivative involved, but there are problems which are gets quite complicated, okay, where you have not only this one variable, but maybe two variables and then there are derivatives and all. So, in those kind of problems, okay, this kind of carrying out this constant energy minimization, that is done by what is known as Lagrangian model. So, what we do is that by use what is known as the Lagrange multiplier. So, in the Lagrange multiplier method, what you do is that you form a function phi. So, in the function you have this ut, that is the total energy that you have, and minus you consider what is known as a Lagrange multiplier lambda into this quantity, that is the total volume, that is the constant over here. So, the total volume will remain constant. So, use this volume. So, this is called that Lagrange multiplier method. So, what we will like to do is we will like to write down. So, this particular quantity phi, okay, this is called the Lagrangian. So, here this u t that we have derived earlier, that is 2 pi r square into, let me write it down, 2 pi r square into 1 minus cos theta into gamma L into gamma L plus this is pi r square, I guess, pi r square sin square theta, pi r square sin square theta into gamma S L minus gamma S plus 80 into gamma S here, 80 into gamma S it should be, yeah, there is a typographical error here, it should be gamma S plus 80 into gamma S, like that, minus I have to have the volume, the total volume that you have here pi r cube by 3, this is gamma into pi r cube by 3 into 1 plus 1 minus cos theta whole square, sorry, 1 minus cos theta whole square into 2 plus cos theta, is that correct? 2 plus cos theta, right. So, that is all is my relation. This is called the Lagrangian, and this Lagrangian will be minimized by considering del phi by del r equal to 0 and del phi by del theta equal to 0, by putting these two quantities as 0. So, here is the whole Lagrangian that I have done. Now, these two equations are called the Euler Lagrangian equation. So, I will first derive it with respect to r, let us say del phi by del r, that will be 4 pi r here into 1 minus cos theta gamma L plus 2 pi r sin square theta into gamma S L minus gamma S. Actually, I have the other quantity with respect to A t also, but that is constant. So, gamma S into A t, that part is constant. So, we have not even written it, but you should write it actually. Okay, minus I have lambda, that is the Lagrange multiplier, into this is pi r cube. So, it is 3 pi r square by 3 here into 1 minus cos theta whole square into 2 plus cos theta. Okay. So, this whole quantity will be equal to 0 here, and now I have the Lagrangian del phi by del theta same. So, I will have to derive it with respect to theta as well. So, here it will be 2 pi r square, 2 pi r square into 1 minus cos theta, so it is 0 minus cos theta sin theta actually. So, sin theta gamma L plus this is pi r square sin square theta will be 2 sin theta cos theta into gamma S L minus gamma S, and minus this is lambda pi r cube by 3, and here I have to derive the whole thing. So, here let us say first derive the first part in the parenthesis. So, it will be 2 into 1 minus cos theta, then minus cos theta is sin theta into 2 plus cos theta here, and plus this is 1 minus cos theta whole square, and this is 2 plus cos theta will be minus sin theta here. Both these quantities are equal to 0 here. So, I have derived it and then I have summarized it over here like this. So, yeah, basically this d phi by dr will be equal to 0. So, finally, we will get this quantity, and then I have these two quantities. So, I have finally let us say this quantity here. Here is another equation. So, this is one equation I have. Another equation, let me just write it. This is 4 gamma L. So, this quantity actually. So, yeah, let me write it here. So, 4 gamma L. So, this is one equation derived, and the second equation I derived from that Lagrange by putting the derivatives equal to 0. So, here you see I can write it like this, 4 gamma L plus 2 into 1 plus cos theta into gamma SL minus gamma S divided by 2 gamma L plus 2 cos theta into gamma SL minus gamma S. So, that is equal to here it will be gamma r into 1 minus cos theta. So, this 2 term will get cancelled. I will be left with 2 plus cos theta by 1 plus cos theta. Okay. This is simple. So, like that. Now, I will use something like this. I am going to here this is the numerator and denominator. So, I will subtract this numerator from the denominator. Okay, I can do that. So, it will be 4 gamma L plus 2 into 1 plus cos theta into gamma SL minus gamma S, and here so minus I will write 2 gamma L minus, let us say 2 cos theta into gamma SL minus gamma S divided by 2 gamma L plus 2 cos theta into gamma SL minus gamma S. So, that is equal to here 2 plus cos theta minus 1 minus cos theta divided by 1 plus cos theta. So, this is equal to 1 by 1 plus cos theta, okay. And we can simplify over here. So, that will be here it is 2 gamma L plus 2 cos theta into gamma SL minus gamma S, and 4 gamma L minus 2 gamma L is 2 gamma L, and here it is plus here it is 2 into 1 plus cos theta. So, let us say 2 into 1 plus cos theta minus 2 cos theta into gamma SL minus gamma S. So, you do little algebra here like this, the one where I am doing here 1 plus cos theta. So, here finally I will have, so 2 cos theta is going to get cancelled here. I will have 2 into 1 plus gamma L. So, I will have 2 into this is gamma L plus this is 1 plus cos theta, 2 into so 2 into, so it is gamma SL minus gamma S divided by 2 into this is gamma L plus cos theta into gamma SL minus gamma S into 1 plus cos theta. So, we can now rearrange this 2 gets cancelled here, and we can rearrange, and that is what we have done here. And finally, I have here after rearranging we will have this particular thing. Okay, we can easily get here like this. So, you can see that we have this liquid drop here, and this liquid drop forms a contact angle of theta, let us say, and this is, or let us say it is theta here, this is theta, here is the tangent over here, and this is gamma S, surface energy here is gamma S, surface energy here is gamma SL, surface here is gamma L. So, we have a balance here, gamma S is equal to gamma SL plus gamma L cos theta. So, what we have considered is that, remember that while doing that we took the energy of this particular liquid drop, surface energy, interfacial energy, okay, and solid surface energy also we took, and we considered that this particular substrate is rigid, that is correct, that I have to mention, this is rigid here, and we do not consider the worry about the gravity. Now, what I can say without giving the proof is that even if you take gravity into a system, that means the liquid drop is large enough that because of gravity it has some amount of deformation. Say because of gravity it has formed something like this, okay. then also the contact angle will remain same, contact angle will not get affected by the gravity. Okay. So, again I repeat that suppose I take a drop that is large enough that gravity becomes important. So, that if gravity pulls it down, so it deforms because of gravity, but then it will deform at the bulk and away from the 3 phase contact line. At the 3 phase contact line, the contact angle that is attained, that will remain independent of that gravity or size of the drop. So, that has been proved by theoretically, I am not going into giving this proof, but that is what I want to tell you, that this is the way it is. But whenever we do this measurements of interfacial energy or surface energy, we try to maintain the liquid drop as small as possible, so that we can neglect the gravity effect and we have the liquid drop as a spherical cap. Now, there is one point that I would like to highlight, that this Lagrange multiplier method that I used here. So, the question is that how did it work, why and why does it work. So, that is the thing. So, let us say that we have this r and theta at the x and y axis, let us say, and the z axis is this ut is the total energy. So, let us say that if I plot this r and theta, this ut as a function of r and theta, I will get a kind of a curved surface like this. So, what is happening is that we are trying to get there and we have this different values. Okay. So, let us say that we are varying r and theta along these lines and we are trying to get there. So, in essence what we are trying to do is that we are finding out the slope of this surface at different points. So, slope of the surface will be represented by how? Will be represented for, let us say, delta ut, that is the slope of the surface at any point, and remember that the slope will be directed towards the vertex or towards the top of this particular surface or hill or whatever you say, it will be like that. So, that is why the slope will be here delta ut. Now, we are not allowed to take any value for n theta because there is a constraint there. So, let us say this is the constraint. So, the constraint is represented by this particular surface which cuts this 3-dimensional surface at these points, at this line, along these lines. Okay. So, we have got this particular constraint here. What it means is that we cannot take any value of r and theta, we have to take the values along this line actually, because that is the constraint. So, when you go take different values of r and theta along this line, so and we calculate the slopes, remember that the slope will be perpendicular to this line. So, it will be slope will be along this line. So, we are trying to go at different locations and the slope changes. Finally, when you reach at this point, the this slope and the this slope. So, slope from this constraint over here. So, let us say that this slope I represent it by delta v, okay, delta v, let us say. This slope and this slope, that their direction matches. Okay. So, then this delta ut and the delta v, their direction matches. So, I can write it delta u as a some kind of constant into this delta v, means the slope of v here. So, when you do that, delta of ut minus lambda into v, okay, that is equal to 0. So, we get like this. So, it is from that concept, that is why, okay, for this constant energy minimization or constant optimization, okay, we can use this Lagrange multiplier method, where this lambda is that particular constant which is called the Lagrange multiplier. So, I will stop here today my discussion on this surface energy and Young's equation. So, I will take it up some problems in the next class. Thank you for your kind attention.